field that we've seen over the last 150 years, it's currently decaying at a rate that would see it disappear in 1,500 years.
Earth's magnetic field is decaying fast. Discovering the consequences for our planet is a top priority. Earth's magnetic field is fading. But what would happen if it disappeared completely? The answer lies on another planet in the solar system.
We're good symmetrical burn on all 6 solids.
In 1996, NASA launches the Mars Global Surveyor. Its mission? To unlock the red planet's secrets.
Coming up on Mach 1.
Of all the planets in the solar system, Mars is the most similar to Earth. Both planets are made from the same materials. They each have hard crusts, dense cores, and relatively similar atmospheric chemistry. Scientists believe that, like Earth, water flowed on Mars's surface. But that was billions of years ago. Today, the planet is a frozen desert. To find out why, the orbiting Mars Global Surveyor collects data from the red planet. Professor Ben Weiss uses this data to reconstruct its past.
Unlike the Earth, Mars today does not have a global magnetic field generated in its core. But if you were to walk around the ancient southern highlands of Mars, you'd be walking in many places in fields as strong as the Earth. But they'd be very complicated, almost like spaghetti, pointing in all different directions, not pointing north at all.
The satellite discovers that certain areas of Mars's crust are strongly magnetic.
It's clear from the fact that the Martian crust is strongly magnetized that there must have been a magnetic field on Mars in the past. Because that's the only way we know to magnetize rocks is for them to form in the presence of a magnetic field.
Why did Mars lose its magnetic shield? And what effect did it have on the planet? To find out, scientists need to analyze Mars's rock. Mars Global Surveyor didn't stop to take samples, but Weiss has managed to get hold of something extremely rare: Martian meteorites.
We have some rocks from Mars that were naturally transferred to Earth. These are meteorites that were blasted off of Mars by an asteroid or comet impact.
Weiss takes the meteorite sample into a special magnetically shielded chamber. He places it in a superconducting quantum interference device, or squid microscope, for analysis.
So the magnetic field of a rock is extremely weak. So in order to do that well, we need to make these measurements in a very weak magnetic field.
This highly sensitive machine measures the exact strength of the rock's magnetism. By analyzing different samples, Weiss builds up a picture of Mars's magnetic field at the very beginning of the planet's existence.
We have actually one rock from Mars that's 4.5 billion years old. And we've actually recently shown, by looking at the intensity of the magnetization record in that rock, that Mars had a magnetic field that was roughly the strength of the Earth today.
Weiss's research reveals that in its first 50 million years, Mars had a strong magnetic shield.
It's amazing the diversity of magnetic fields that we see above different samples. Some of them, like this one, this is an ancient rock from Mars that's 4.5 billion years old. You only see tiny little isolated magnetic anomalies with huge areas of non-magnetic rock in between.
Why Mars lost its shield is a mystery, but what happened to the planet as a result is not.
When Mars lost its magnetic field, it lost its shield that was protecting it from the solar wind and from cosmic radiation, and that had consequences for the evolution of its atmosphere.
The weak magnetosphere allows solar wind to strip away Mars's delicate atmosphere. Its oceans vaporize, temperatures plummet, and any primitive life forms die. The loss of the magnetic field has a catastrophic impact on the planet's evolution. Mars becomes the red planet we see today. If Earth's magnetic protection continues to fade, will it suffer the same fate? Earth's magnetic field is weakening fast. If it vanishes completely, the planet might end up like Mars.
How have Earth and Mars evolved differently such that Earth still has a field and Mars doesn't? Actually, the problem at the moment is more one of explaining where the energy is coming from that powers the Earth's magnetic field.
To find out exactly how and where our magnetic field is generated, scientists need to explore Earth's interior. But this isn't easy.
We really don't know a lot of detail about what's happening 2,000 miles down because there's no way to send a probe there.
Since there's no way to probe it directly, scientists study the structure of our planet using one of nature's most powerful phenomena: earthquakes.
So the seismologists, they wait for an earthquake, let's say in Japan, and then they put an array of detectors on the other side of the Earth and look for the sound going through the Earth. And by listening carefully, they can construct a map of what's inside the Earth.
Scientists measure earthquake vibrations called seismic waves. These waves don't travel through the planet in a straight line. Instead, they bend, changing speed and direction when they pass through different materials. By measuring these waves carefully, scientists learn that Earth must be made up of distinct layers, like an onion. The surface layer, the crust, is made of solid rock just a few miles thick. Below sits the mantle. It consists of denser semi-liquid rock. 1,800 miles down is the liquid outer core, a churning sea of molten iron and nickel. It surrounds the inner core, a solid iron sphere around the size of our moon that is as hot as the surface of the sun. Scientists believe that the magnetic iron core generates our magnetic field. But how?
People are easily confused by this idea that there's this big solid iron inner core, so thinking it's just a bar magnet, it's just a permanent magnet frozen in that, and that's what causes all the magnetic field. But it's too hot inside the Earth. That can't happen. When the temperature gets hot enough, magnets turn off.
Permanent magnets stop working at 1,200 degrees Fahrenheit. So some other process must be generating Earth's magnetic field. To find out more, Professor Don Lathrop embarks on a very ambitious experiment. At the University of Maryland, he and his team build a 10-foot mechanical model of the Earth's core.
The thing we want to understand is why some planets generate a magnetic field and why others have no magnetic field. So by building experiments, we could hope to understand the conditions of when it works and when it doesn't. What's the switch? Why sometimes a planet comes alive magnetically and why sometimes they remain dead.
Inside the sphere is a solid iron ball, surrounded by 13 tons of churning liquid metal. Lathrop uses molten sodium instead of iron because of its lower melting point.
So we've got a rotating outer sphere, holds liquid sodium. It's meant to mimic the iron in the Earth's core.
Separate motors spin the inner and outer cores to mimic Earth's rotation.
Those drive the outer sphere up to about 4 revolutions per second.